Okay, so this week we're looking at hypothesis testing. And hypothesis testing kind of builds off of that idea of confidence intervals, where we construct a confidence interval. We assume that once we've constructed that confidence interval, that there is a whatever percent. If it's a 95% confidence interval, there's a 95% confident that contains the true population mean. So if we take another sample, or let's say we've made a statement about the population mean, and that statement about the population mean is not within that confidence interval. So we generally would say, hey, we're 95% confident that that statement of the population mean is not correct because we constructed this confidence interval and it's not in it. So let's take a look at what we're looking at here. So the first thing that we have to do with any sort of hypothesis test is define the null and alternative hypotheses. And then we're going to have to gather data and perform the test and then state some conclusions. Then we're going to look at different errors that can happen in those tests. So defining the null and the alternative hypotheses. Now the null hypothesis is always the status quo. In other words, if there's an accepted standard, that's out there. Or what's against our own best interest. So if someone else makes a statement and we're trying to disprove it, that their statement, the other person's statement, becomes the null hypothesis. If we say, hey, we're studying to see if more people are catching the flu now than they were 10 years ago, the null hypothesis is the same amount or less are catching the flu now than there were. So let's look at the null and alternative hypothesis. So we got a study published by the Journal of the Air and Waste Management Association. Reported that the mean amount of particulate matter, PM, produced by cars and light trucks in an urban setting is 35 milligrams of particulate matter per mile of travel. Suppose that a new engine design is proposed that is intended to reduce that amount of PM in the air. There are two possible outcomes that could happen with the new engine. Either the new design will reduce it or it will not. So that's the thing about hypothesis testing, is you have to be down to two possibilities. Either it falls in this category or it doesn't, or either it meets this qualification or it does not. These possibilities are called hypotheses. So one of them is called the null and the other is the alternative. The null means nothing happens. We don't change anything. Alternative means the accepted has evidence against it. So what is the alternative to what's been accepted? So the null hypothesis is about a parameter, about the population parameter, either usually a mean or a population proportion, and is denoted H0. H naught is what they usually say. HO, but it's really a 0. H0 is in the null. 0 is the null set. The alternative hypothesis is about a parameter. Again, same parameter as the null hypothesis. And what it does is it states different from the null. And what that means is the null and the alternative have to cover every possibility. So the null says this, the alternative says everything else. So the alternative hypothesis is denoted by H1. And now that could change. Some books call them H0 and HA for alternative. This one's using H1, H0 and 1, which does make sense. So there are several possibilities here. One is there's a left-tailed test, and the alternative hypothesis determines the tail. So we're thinking about that bell curve again. I'm going to draw it up here. And what we're looking at is we're trying to find, let's say that we know that the null hypothesis is stating that it's a certain value. The population mean is a certain value. The alternative says that we think it's less. The alternative would be less than that value. So we'd reject down here on this tail. That's a left-tailed test. That states that the parameter is less than the value specified by the null hypothesis. So if we get a small enough result in our test, in our sample, then we're saying, hey, that's so small that the confidence interval constructed around that sample mean would not contain that hypothesized mean. So therefore, we're pretty confident that hypothesized mean is not correct, or we're going to reject it. We're not saying that it's wrong. We're not saying that it's right. We're saying we've got strong enough evidence to reject it, or we don't have strong enough evidence to reject it. Right-tailed test is going to be just the opposite. We've got our curve here, and in a right-tailed test, we're saying that the null is claiming that it's at or below a certain value. So we're going to reject it if we get a sample that has a too large of a value. And again, if we get a sample mean that's so large that our confidence interval around that mean does not include our hypothesized value, then we say, hey, we're 95% confident the hypothesized value is not true. Then a two-tailed test is we're saying that the null hypothesis is saying that the mean of the population is exactly at the middle, not bigger or smaller, or at least or no more than. It's exactly that value. So then we can reject it if we get a value that's either too small or too large. So we're rejecting on both tails. And what goes in here is alpha. Alpha tells us what probability is on that tail. So for the lower tail or left tail, it's there. Upper tail or right tail, that's there. For the two-tailed test, alpha gets split half to each tail. So the study published in the Journal of Areas Management. Okay, so same, I'm not going to read it again, same situation we had before. We're going to look, oops, that's why I went back instead of forward. So boxes of a certain kind of cereal are labeled as containing 20 ounces. An inspector thinks that the mean weight may be less. State the appropriate null hypothesis. Null and alternative hypotheses. Now the inspector thinks it's going to be less, but the inspector's testing. So we're going to, the null hypothesis, H0, is always to claim that the status quo is just fine. So that the mean is equal to 20 ounces. Now technically, some books would say greater than or equal to, so it's at least 20 ounces. This book does it this way. It's implied, and I'll show you why here in a second. So alternative then is that the mean is less than 20 ounces. So when we see that this says less than, we're implying that null hypothesis means greater than or equal to. Because remember, they have to cover all of the possibilities. But for this textbook, and there's a couple of different fields in statistics that do hypothesis testing slightly differently. And this is the one where the null hypothesis is always stated as equal to. Then the alternative hypothesis states less than, greater than, or not equal to. So it picks the tail. So when we see that in the alternative hypothesis saying less than 20, that's implying that null hypothesis really was greater than or equal to. So those are hypotheses for this situation. So now last year, the mean monthly rent for an apartment in a certain city was $800. The real estate agent believes that mean rent is higher this year. So again, the appropriate null hypothesis is that nothing has changed. Is that the mean rent is equal to $800. The alternative then is what the realtor is trying to say, is that the mean is greater than $800. And again, when we see this here, where the alternative is saying greater than, that's implying that the null was less than or equal to. Scores on a standardized test have a mean of 70. Some modifications are made to the test, and an educator believes that the mean may have changed. So now they're not saying is increased or decreased. They're just saying it may have changed. So the alternative, again, is that nothing has changed. The mean is still equal to 70. Or the null, I should say. The null hypothesis, again, that nothing has changed. The mean is still equal to 70. Our alternative, then, is the educator's belief that the mean is not equal to 70 anymore. That's changed. So this is a two-tailed test. We're going to reject if we get sample results that are either too small or too large. So when we're doing a test, we always assume that the null is true. So we're making this assumption that the null hypothesis is true. And then we look at what the probabilities would be based on that. So we take our sample and we use the sample data to construct a confidence interval, basically. And if that null hypothesis is outside of that confidence interval, well, then we're looking at saying, oh, maybe that assumption is wrong. And one way of doing a hypothesis test is actually just to construct a confidence interval. But we switched it around to make it a little bit more precise than that. So then we look at the evidence after we make those hypotheses, and then we make our decision. So let's state our conclusion. So we've stated our hypotheses, we've gathered the evidence. The way we word our conclusion is very, very important. We never want to say accept the null hypothesis. You can either reject it or fail to reject it. So here we rejected the null hypothesis. We had enough evidence to say to strongly discredit that null hypothesis. We're not saying it's wrong, we're just saying we've got enough evidence to reject it. Because there is still a slight chance that it is correct, that we just had a really outrageous sample. Now, if the null hypothesis is not rejected, there is not enough evidence to conclude that the alternative hypothesis is true. So what we're saying, we're not saying the null hypothesis is true, so we never ever use the wording that we accept the null hypothesis. That's never the case. We just failed to reject it. We failed to gather enough evidence to say it's incorrect. But remember, we're stacking the deck in favor of that null hypothesis. So we have to have really extreme evidence to reject it. So we didn't prove it true, we're just saying we don't have extreme enough evidence to say it's incorrect. So back to the boxes of cereal, we've got our hypotheses, the null hypothesis saying that it's equal to 20, the alternative saying that they're coming in light, they're less than 20. We reject the null hypothesis here. He rejects the null hypothesis. So our statement is, we reject the null hypothesis, and we conclude the alternative is true, which means we conclude that the mean weight of the cereal is less than 20 ounces per box. So there it is. Okay, next we're going to distinguish between the types of errors. So looking here, a type 1 error is when the null hypothesis is true, but we reject it. So a type 1 error is rejecting a true null hypothesis. That's right here. HO is true, but we reject it anyway. A type 2 error is much more common. A type 2 error, that the test is actually stacked in favor of a type 2 error, that HO is really not true, but we failed to reject it. Because again, we said we stacked the deck in favor of the null hypothesis. So the dean of a business school wants to determine whether the mean starting salary of graduates at her school is greater than $50,000. She'll perform a hypothesis test with the following null and alternative hypotheses. So the null is that the mean is equal to 50,000. The alternative is saying greater than. So again, that's implying this is less than or equal to here. But suppose that the true mean is 50,000 and the dean rejects HO. Is this a type 1 or a type 2 error? It's type HO is true and the dean rejects it. If you go back here, HO is true and it's rejected is a type 1 error. So here now, let's say that the true mean is, this is the same problem. Okay, so suppose that the true mean is 55,000 and the dean rejects HO. Is this a type 1 or type 2 error or a correct decision? Well, the mean really is a bit higher than 50,000, so this would be the correct decision. There's no error here. Next example here, suppose the mean really is 55,000, so it's greater than 50,000. But the dean fails to reject HO. So if the null hypothesis is not true and you fail to reject it, that's a type 2 error. So we've seen how to write the null hypotheses. We've determined which type of test it is, whether it's left tail, right tail, or two tail. We've looked at how we state the conclusion, and we've looked at the types of errors. So the next step is we're going to actually start looking at the testing process itself. So I'm going to pause this while I pull up the next. Okay, so now let's look at the hypothesis testing process. We're testing a population mean, and just like with our confidence intervals, there's a difference between if we know the standard deviation or if we don't know the population standard deviation. So this first process is we know the population standard deviation. So we're going to look at performing the test with the critical value method, performing the test with the p-value method, and we're going to look at describing the relationship between the two tests. The two should always give the same result. They're just, the p-value method is actually just going one step beyond, using probabilities rather than just finding the cutoff. Describe the relationship between alpha and the probability of error, and then report the p-value or the test statistic. We'll also look at distinguishing between statistical significance and practical significance. So performing a hypothesis test with a critical value method. So the critical value, when we're looking at that curve, remember we're looking at the normal curve. And let's say it's a left tail test. So we're going to reject if our sample mean is too small. So we're rejecting on that left tail of the curve. The critical value method is saying we're taking this probability here is alpha, and we're finding the z-score that corresponds with that cutoff there, that boundary. That's our critical value. So in the previous section, we talked how to construct the hypothesis test and the conclusions. Now we're going to actually perform the test. So critical value and p-value methods are the two methods we're going to use. In a hypothesis test, the idea is to select a sample, calculate a statistic such as x bar, and compare it to the value of the null hypothesis. If the difference between them is significantly large, it is less likely to be due to chance. If HO is less likely to, and HO is less likely to be true. Otherwise, a small difference may be due to just random chance. So that's just it. Just because we say in HO, we say that the mean of those boxes, in H0, the mean is equal to 20. If we take a sample and get 19.8 ounces, that doesn't mean that it's not true. It's got to be significantly smaller before we can say it's true, because there's just a chance that we got one or two really small boxes in our sample that threw it off, or we just happen to randomly select boxes that were smaller. The true mean really could be larger than that. So the whole idea of confidence, the whole hypothesis testing is figuring out how big does that difference have to be before the likelihood is that it's done by random chance is so small that we're going to say, nah, it must really be a flaw with the null hypothesis. So we're looking at how strong that disagreement is between the sample mean and the hypothesized means. So in this example, we begin. The College Board reported that the mean SAT score in 2009 was 515, a standard deviation of 116. Results of an earlier study suggested that the coached students would have an SAT score of approximately 530. So the teacher who runs an online coaching program thinks that students coached by this method have a higher mean score than this. So the teacher believes that the score is 530. So that's going to become the alternative. The null is that the score really is 530 if they're coached. And the alternative is what the teacher's saying is it should be more than 530. So the teacher draws a random sample. It has to be a simple random sample of 100 students who are planning to take the SAT and enrolls them in the online coaching program. After completing the program, their sample mean SAT score is 562. Well, that's more than 530. But is it enough more so that we can prove our point? That we can say, yep, all students who have been coached are more than that. And then we have to see. So this is higher than the hypothesis. And to be determined how strong that disagreement is, we calculate a test statistic. So that test statistic is a z-score of the sample mean based on our hypothesized value. Notice we're assuming the hypothesized value of the mean is true. And we are using our standard error of the means rather than the standard deviation. So that's the population standard deviation divided by the square root of the sample size. Now, when I first looked at this, I would have said this should be 530 here, because that's what was the hypothesized value. So personally, I would put 530 in there. So this is going to be a little off. But anyway, they mistakenly put in the 515. That's not the hypothesis. What has to go here is what's the null hypothesis. So anyway, calculate the value of the test statistic, which is just the z-score of the sample mean, which is the population standard deviation of 116. And we get the z-score. So compared to the actual population of all students, it's 2.76, which is going to be way out here. So, but now notice they put in the 530 in the middle here again. So That's where I would have done it. Now I'm just going to double check their calculation here, just to see if they actually did use 530 and just mistyped it. So let's try that again. There, we got it to work. So 2.7. So they actually did, they just misprinted. They actually did use 530 there. 2.76 is still the z-score, the test statistic, even with that 530. So that's just a misprint. That should not say 515 there. Okay, so this is 530 is in the middle of our curve. What we got from our samples way out here, 2.76 standard deviations or standard errors above the mean. That's our test statistic. So now if we had a critical value somewhere, we'd have to know a confidence level and alpha and all that. We would establish a critical value. So we'd have to have that critical value to compare to it. So the critical value method is saying, now also, by the way, look at this, and there's a probability out here of being further out. This value cuts off this tail. We want to know the probability of that tail. So that would be the p-value method, is that taking that probability and comparing it to the p-value. The critical value method is finding where that cutoff would be for our alpha level. So here's our critical value. We need to find that critical region out here. This is a upper tail test because the alternative is greater than. So we need to figure out where that cutoff is here. Now we haven't stated an alpha or a confidence level, so we have no way of finding that right now. And here it's saying alpha. Whatever this probability is out here is going to equal alpha. So alpha is defining that probability of this tail. So we use alpha here, and then our normal distribution to find out what that z-score is for that tail, what that critical value is. So let's say this is a 95% test. So alpha is 0.05. So this probability is 0.05. If you do an inverse z, so clear this out. Second, distribution, inverse normal. That's 0.05, so that means that remember the calculator's looking at less than. So we're looking, this is the 0.95 spot here. 1.6448, so 1.645, which is what we have for our critical value. Now our test statistic of 2.76 is way out here. It's way beyond the critical value. So this is saying that there is enough evidence to reject that null hypothesis and go in favor of that alternative, that most likely the student scores of coach students is greater than 530. Location of the critical region depends on whether the alternative is left, right, or two-tailed. So like we said, this one, since the alternative was saying, if H1 is saying the mean is greater than a certain value, then we're looking at an upper tail. Less than lower tail, and then, of course, two-tail would be not equal to. So this is just a little table of our significance levels. Alpha is called the significance level based on that level of confidence, and whether it's one tail or two tail. Notice left tail or right tail is always the same number, just one's negative, one's positive, because the left side of the curve is negative z-scores, the right side is positive z-scores. Two tail, there's always going to be two values, one positive, one negative, and they will be the same, just one's positive and one's negative. So the assumptions, we have a simple random sample, and either the sample is greater than 30 or the population is approximately normal. So if we don't know that the population is approximately normal, we have to have a sample of at least 30 or more. So first, we're going to state the null and alternative hypothesis. We went over how to do that. Choose the significance level. It's very important. Before we gather data and performing a test, we must set the parameters of the test. We must set the significance level and alpha and find those critical values before we start analyzing data. Then we can compute the test statistic and compare it. determine whether we're going to reject or not reject, depending on what our alternative hypothesis is. So an example, the Energy Information Administration reported that the mean price of a gallon of regular grade gasoline in the city of Los Angeles in July 2010 was $3.15. A recently taken simple random sample of 50 gas stations in Los Angeles had an average price of $3.10 for a gallon of regular grade gasoline. Assume that the standard deviation in price is 15 cents. An economist is interested in determining whether the mean price is less than $3.15. Use the critical value method to perform this test. So, of course, we must first set up our hypotheses. HO is that the mean price is $3.15. HA, the alternative, is that the mean is less than $3.15. Now we have to set a significance level. They set it for us at 0.05. So what this is saying is, here's our curve. The alternative hypothesis is less than, so we're going to reject on the lower tail here. And that probability of 0.05. So if we do an inverse normal here of 0.05, we should get a negative 1.645. So that critical value is a negative 1.645. Now we check the assumption. This is randomly distributed in our sample size. We do have a simple random sample we're going to have to take. So our sample size, if the population is normally distributed, it doesn't have to be greater than 30. We can't be sure of that, so we're going to make sure our sample is greater than 30. So we made our hypotheses just as I showed you. Our significance level of 0.05, we found our critical value to be negative 1.645. The population standard deviation is 0.15. So we know the population standard deviation. Since we assume HO to be true, we're going to use that as the population mean of 315. So we're going to create our test statistic here. 310 is the sample mean, minus 315, which is the population mean, or the assumed population mean from our hypothesis. Taking our standard deviation of 0.15 divided by the square root of the sample size, n was 50. That gives us a critical value of negative 2.36. Now remember, we're looking at a curve like this. Our cutoff here is negative 1.645, and we're rejecting if we're out here. Well, negative 2.36 definitely falls out there. So we are going to reject the hypothesis. So we conclude that the mean price of gas is less than 315. We can't say that it's 310, but we can say that it's less than 315. There's adequate evidence to reject the null hypothesis and conclude that the gas price really is less than 315. So let's look at the p-value method. The p-value method, what we're looking at here is simply, we're still looking on the curve, and we know that alpha is describing this probability out here. So then we do our test and we decide, well, what's the probability that we're going to get a value less than? Assuming that the null hypothesis is true and that hypothesized value of the mean is true, and assuming we were given that population standard deviation. So what's the probability of getting a score, since this is a lower end test, a lower tail test, what's the probability of getting a value of our sample mean less than that, and comparing that probability to alpha? Or if it was an upper tail or right tail test, what's the probability of getting a score, a value greater than that, and comparing it to alpha? So here we go. P is the probability that a different drawn, sorry, P is the probability that a number drawn from a distribution of the sample mean would be as extreme as or more extreme than our observed value. So unlike the critical value, p-value tells us exactly how unusual the value is for our sample mean. For this reason, the p-value method is often used in practice. So we can actually say, hey, less than this percent or less would experience this value. So the smaller the p-value is, the stronger the evidence is. So we're dealing with p-values. It's always if the p-value is less than alpha, we will reject. So here's our SAT scores again. alpha is 0.05. We've got this value of 2.76. What's the probability of getting a z-score of greater than 2.76? 0.00289. So it's really small. It's a p-value of 0.0029 is less than alpha of 0.05. So then we would reject. So the smaller the p-value is, the stronger it is, the more significant it is. So if we chose our level of significance, and for that test we had a 0.05, if our p-value is less than that level of significance, if the p-value is less than alpha, we reject the null hypothesis. If not, if p-value is greater than alpha, then we do not reject the null hypothesis. Suppose you found the p-value of 0.012. Do you reject at 0.05? Yeah, that's less than 0.05, so yes, we reject. Would you reject at 0.01? Well, no, 0.012 is not less than 0.01, so no, we would not reject at that level. So the mean height of adult men in the U.S. is 69.7 inches with a standard deviation of 3 inches. Sociologists believe that taller men may be more likely to be promoted to positions of leadership. So the mean height mu of male business executives might be greater than the mean height of the entire male population. Simple random sample of 100 male executives has a mean height of 69.9. Now again, just because the sample mean is higher than the population mean does not mean that there's really a difference there. It has to be significantly larger. So assume the standard deviation in the males is 3 inches. Can we conclude the male business executives are taller on average? So first we got to create our hypotheses. HO is that the mean is 69.7, the same as our population mean. The alternative is that the mean is greater than 69.7. So then, level of significance we've got to set, they've given us 0.05. So now since this is greater than, the alternative is greater than, we would reject on the upper tail, up in here. Alpha is 0.05, so that's that probability. So if we get a p-value of less than 0.05, the value of getting something larger than 69.9 is less than 0.05, well then we've hit the significance level, and we would reject. So let's just do a normal distribution here. So normal CDF is 2. We're going to go from 69.9 to positive infinity. I'm just going to use the 6 nines as the positive infinity. I know your textbook uses 1E99. With a mean of 69.7 and a standard deviation of 3 divided by the square root, because remember we're taking a sample here, so it's the square root of the sample size, of 100. Let's get a probability. 0.25. Well, that is not less than alpha, so we would fail to reject here. The sample here does not give a mean height large enough to say that it's significantly different than the population mean. So let's go through what the PowerPoint is saying, what their steps are. So they get our the means we got here, the null and alternative hypotheses are the same here. Level of significance was given as 0.05. Now they did the test statistic, we did not. We just found the probability of the result, but they get the test statistic. Then doing the p-level. For that z-score, they're using the standard normal curve. We just use the normal distribution. That's exactly what we have, 0.2514, 0.2524. They had little round-off errors in their z-score is all. Interpret the p-value. Since the p-value is not less than alpha, we fail to reject HO. So example time again. At a large company, the attitudes of workers are regularly measured with a standardized test. The scores on the test range from 0 to 100. The higher the scores indicate greater satisfaction with the job. The mean score overall in the company employees was 74, standard deviation of 8. Some time ago, the company adopted a policy of telecommuting. Under this policy, workers could spend 1 day per week working from home. After the policy had been in place for some time, a random sample of 80 workers was given the test to see if their mean level of satisfaction had changed. The sample mean is 76. Assume the standard deviation is 8 is true. So we're going to do the mean test the means here for alpha of 0.05. So again, we're going to have null hypothesis is that the mean is still equal to the old, what the old one was 74. The alternative is that the mean is greater than 74. So on our curve, again, we're rejecting on the upper end here. This probability is 0.05. Now again, I can just use normal distribution here and find my p-value. Second distribution, normal. I'm going from 76 up to positive infinity, so 1 E99. I'll do that consistent with the book here. With a mean of 74 and a standard deviation of, it says 8, but remember it's 8 divided by the square root of our sample size, which is 80. Which gives us 0.0127. That is less than our confidence level, so we are going to reject here. Now, the way the book does is it's going to calculate the test statistic to 2.124. My advice, if you're going to do the test statistic, you should just find the critical value anyway. But they do have the 2.24 as a test statistic, which is pretty high. I mean, any test statistic beyond 2 is usually, unless we have an extremely low level of significance or high confidence level. Generally, if it's beyond 2, we're going to most likely look at rejecting for a test for the means or proportions. But anyway, we've got our test statistic. We're going to find the p-value. Now they're saying here they're using the hypothesis that it's different than 74, not that it's increased. So I did that it increased. So if they're doing different, well then they're dividing up alpha to different both sides of the curve. So our p-value would actually change. Our p-value would actually double that. And I'll show you what I mean here in just a second. So they're saying since they're using that hypothesis that it's not equal to, so it's a two-tailed test. So we're rejecting on both tails of the distribution. So they're finding alpha of 0.05. It's going to be 0.025 here, and this will be 0.975, the 2.5% on each end if we get our critical values. And we'd find that would be 2.24 and negative 2.24 for Z. So if we're going to use the critical value method, we had a test statistic of, get back here, 2.24. Oops, sorry. What we're putting in here is the test statistic of 2.24, not the critical value. So our test statistic is 2.24. So since this is a two-tailed test, we have to find the probability of being more extreme on both ends, both tails. So 2.24 and negative 2.24. And we see what the probability of being outside of that is. So we find this probability and this probability, and we add them together. So the probability of being greater than negative 2.24 is 0.0127. So it's 0.0127 out here and 0.0127 out here if we find the probability of being less than the negative 2.24. If we add those together, we get 0.025, about 254. And they're saying 0.0250, so there's some rounding errors again. Since their p-value is less than alpha, we're still going to reject. So even though it was a two-tailed test and not a 1, we still are going to reject that. So our conclusion is we conclude that the mean score among employees has changed since the adoption of telecommuting. So now let's go back here and see where I screwed up in creating my hypothesis. They asked the question here, can we conclude that the mean level of satisfaction in the policy, it says, can we conclude that the mean level of satisfaction is different? Okay, so that's what they're asking. Is it different? They didn't ask, is it greater or is it less? It's saying different. So different would be not equal. So that's very subtle. So you can see there, I messed that one up looking at it. So there's some very subtle things in the wording that tell us that. Personally, the reason I jumped to that is I would have probably said, I'm more concerned about increasing employee satisfaction, so I want to see if it's increased. I don't want to know if it's gone down. I want to see if it's gone up, which would make the test a little bit more defined for me. Okay, let's move on here. This is doing it on the calculator. And so on the calculator, we would have entered stat over to tests, and this would be a z-test. Again, we've got the statistics. We don't have our data put in. So our mean here, we're looking at, the mean was 74 from before. Standard deviation was 8. The sample mean is 76. And our sample size was 80. The alternative here, this is what this is asking, is the alternative is not equal to. So I got to select not equal to. Now notice it doesn't ask for a confidence level, because it's going to give us mostly the p-value. Now it does tell us the test statistic is 2.236, or 2.24 is what we had. And the p-value is 0.0253. So we can just say the p-value is less than 0.05, so we can reject the null hypothesis. So when using the calculator, I find it's way easier to use the p-value method because you don't have the critical value. You have the test statistic, but you don't have the critical value. So the calculator is really geared around the p-value method. If you want to do a critical value method, you got to do a lot of that work by hand. So let's do another example. Let's see if I can get this one right on the first try. At a large company, the attitudes of workers are regularly measured with a standardized test. So it's the same one here. So saying, can we conclude that the mean level of satisfaction is different? Okay, so they're doing the same example again, using the calculator, just entering it in the calculator. So we've already done that. So let's move on. Let's describe the relationship between hypothesis test and confidence intervals. So this is what I had said before. We have that null hypothesis. It states that that alternative, or that population mean was 74. Well, we take a sample. So we're going to assume that the mean on the number really is 74. But now we take a sample, and the sample mean gives us 76. And we construct a confidence interval around it, and that confidence interval around it does not include the 74. Since it does not include the 74, we're saying either we took a really, really bad sample, or the 74 must be incorrect. Well, depending on our confidence level, this was a 95% test, or alpha was 0.05. So we're 95% confident that that interval should contain the true population mean. So we're going to conclude that most likely this assumption was not right. So looking at the previous example, we had 74. Doing so, we are saying that 74 is not we rejected that. So by doing that, we're saying 74 is really not a plausible value. We construct the confidence interval based on our sample. This is what we get. 74 is not in that interval. So that agrees with our test, saying that 74 is not in the confidence interval. It's unlikely that 74 is the true value of the population mean. Describe the relationship between alpha and the probability of error. Well, alpha is your probability of a type 1 error. The probability that you will reject the null hypothesis, even if it is true, is going to be alpha. I mean, we have to leave that door open, otherwise we'd never reject anything and nothing would ever change. The smaller alpha is, the less likely that we will commit that type 1 error. Alpha is the probability of a type 1 error. So making it smaller means that we're protecting the null hypothesis. So if it's something really critical where we have something that we know is working, like in medical drug testing, we have a drug that we know is working, and we want to test to see if this drug is better, well, we're going to make alpha really small, because we don't want to replace this drug that is already working unless we are absolutely sure this new one is better. So by setting alpha really small, then we're again, stacking the deck in favor of the null hypothesis. So report the p-value or the test statistic. Sometimes people will report only the result, that it was significant or not, so that either we rejected or did not reject or failed to reject the null hypothesis. There's a big difference between a p-value that is just barely small enough to reject and one that's extremely small. For example, this test we had alpha of 0.05. We had a p-value of 0.049. We just barely rejected it. But if we have a p-value of 0.0001, that means we weren't even close. We way blew it out of the water. We really rejected it. There was no chance of this one not being rejected. So that's saying that it's not only is the null hypothesis unlikely, it is extremely unlikely. So remember, the p-value is telling you what is the probability that the null hypothesis could actually be true and that this is just a bad sample. Well, here this is less than 1/100%. This is 4.9%. So we had to set that cutoff somewhere, and 5% is the most common cutoff. But whether we just barely squeaked outside of it or if we are way out there. And the other way around as well. If we get a p-value of 0.051 and we fail to reject, well, reporting that p-value is showing us, hey, we didn't reject the null hypothesis. We didn't have enough evidence, but we were really close. So maybe this is something that we should look into further. Maybe perform another test, larger sample or whatever, and see, keep looking at it, because yes, we didn't reject it, but there's a possibility out there. Or if we get a p-value of like 0.2, well then we weren't even close to rejecting it, so this is a dead issue. Again, one of the reasons they give for reporting the p-value is you selected the significance level, and that's kind of arbitrary. So somebody else could look at it and say, no, I would have selected a significance level of 0.01. Well, in that case, they would not have rejected if the p-value was 0.049. But they still would have rejected if it was 0.0001. So reporting that p-value allows other people to make decisions based on what their level of importance or significance is. So in using the critical value method, you should always report the values of the test statistic rather than simply stating whether the test statistic was rejected. So just like with the p-value, you should always state the p-value. Same with the test statistic. Give the value of the test statistic so that whoever is looking at it can compare it to your critical values and see whether you were close or whether it was way out there. So statistical significance and practical significance. What we've been looking at in these tests is called statistical significance. If that p-value is not less than alpha, it is not statistically significant. If the test statistic is not beyond the critical value, it is not statistically significant. So when a result has a small p-value, it is statistically significant, like I was saying. Sometimes statistically significant results do not have any importance or practical significance. For example, raise the scores by 2 points on a 100-point scale. The improvement may have statistical significance. We've proven that there was a change, but it's really not important enough to train teachers in that new technique. Only 2 points is not really enough to justify the expense. So there are times where that, even though there's a statistically significant result, it's not practical to take any action on that result. So this is the things that we learned in this section. I'm sorry I kind of stumbled through it a bit. I'm a little bit tired today. But we have now that general knowledge of hypothesis testing, and our next step is going to be to look at hypothesis testing for the population mean if we do not know the population standard deviation. So I'm going to pause here and I'm pull up the next. So as promised, this is when the population standard deviation is not known. So again, we have two types of tests. We have critical value and p-value that we're going to look at. Just like with the confidence intervals, we're not going to be able to use the z distribution or normal distribution. We're going to have to use that t distribution again. So let's look at p-values. So the same type of thing is going to happen. We're going to calculate a test statistic, only now you can see it is a t statistic instead of a z statistic. Because we're not using that normal or z distribution, we're using a t distribution. And recall that in the t distribution, we have to find critical values using degrees of freedom. And there's our probabilities as well. So our p-values are going to be, we're going to have to use degrees of freedom to calculate those values. So the assumption for performing a hypothesis test about the mean when sigma is not known are, well, we have a simple random sample, that's always assumed, and either the sample is significantly large or the population is approximately normal. So if they are met, we may use either method. So first, let's look at the p-value method. Again, same thing as before. Depending on our null or alternative hypothesis, it'll determine what tail we are testing on. And that's what we use to The p-value for a left or a right tail test is just the value of being less than or greater than that test statistic. For a two-tailed test, we've got to do both ends. We've got to take the test statistic and its opposite and find the value of being outside of those values. So here we're going to look at an example. In a recent medical study, 76 subjects were placed on a low-fat diet, low-fat diet. After 12 months, their mean weight loss was 2.2 kilograms, with a sample standard deviation of 6.1 kilograms. Notice it says sample standard deviation. Nowhere in this problem does it say population standard deviation. So that means we do not have the population standard deviation, so we have to use that t-test. So can we conclude that the mean weight loss is greater than 0? So, again, our hypothesis, and all is that the mean is 0. The alternative, can we conclude that it's greater? So we're going to ask, is it greater? So the alternative is the mean is greater. Choose the level of significance. We gave that as 0.05. Compute the value of the test statistic. So we had 2.2 pounds compared to a null hypothesis of 0 over our standard deviation. We're using the sample standard deviation divided by the square root of our sample size. So we get a test statistic of 3.14. Now we don't know the critical value, and we're going to have to use a t-distribution to find that critical value. So here they're going to find the p-value first. So we've got our test statistic of 3.144. We want to know this is a right-tailed test because the alternative was greater than. So we are rejecting on the right tail or upper tail. So we need to find the probability of being greater than 3.144. Now, the 75 here is degrees of freedom. Remember, the sample size is 76. 76 minus 1 would be 75. That's why they put that in there. The second distribution, we're going to use the t-distribution. That's t-CDF is 6. We're going from 3.144, comma, infinity, so 1e99, comma, with 75 degrees of freedom. Sample size of 76, so 76 minus 1 is 75 degrees of freedom. 0.00119, which is what they got. 0.0012, I'd probably round that to, which is what they did. That p-value is less than alpha of 0.05, so we will reject HO. So our conclusion, we conclude that the mean weight loss of people who adhered to this diet for 12 months is greater than 0. Now we could use the tables for p-value with the calculators and Excel and stuff. Generally don't have to rely on that anymore. But you could use the tables to find the p-value. 60, remember we're going to go down, so we have 75 degrees of freedom. We'd always go down to the lower one, which would be 60. Look that up. It's 0.05. If it's a one tail, now looking at here, is this thing 1 or 2? Okay, so this is saying if the upper tail probability is 0.0025, it's 2.91. We're looking at upper tail probability of 0.05, so it would have been 1.671 is what our critical value would have been. Because alpha would be the upper tail for that table. Okay, now what we found, our p-value is between, our test statistic was 3.144. So looking at this table, 3.144 at 60 degrees of freedom falls between these two numbers. So that tells us our p-value is between 0.025 and 0.0025 and 0.001. We can't get an exact value off the table for p-value. So that's why having the calculator or Excel is very, very helpful for the p-value method. Estimating the p-value from a table for two-tailed. So we found it. We found this is our test statistic. The nearest numbers on the table for the degrees of freedom that are closest to 75 are actually closest without going over, so we had to use the 60. We found those two values, two critical values in there. So then we got the probability for each of them. We know we're between those two probabilities. This is just using the calculator for the test. We're going to do stats, test, t-test. Our hypothesized, again, we're using statistics. We don't have the data in the list. Our hypothesized value is 0. The sample value is 2.2 pounds, is the sample mean. Sample standard deviation was 6.1 pounds. Sample size was 76. Now we are looking at alternative was greater than, so we're going to select greater than here. And hit calculate. And there it is, our test statistic of 3.144. It also gives us the p-value of 0.00119 or 0.0012. So we've got both of them right there for us. And this is just explaining the conclusion from the calculator. So finally, test a hypothesis about a mean using the critical value method. So if we wanted to find the critical value, we use that table, or we could use the calculator to find that value. It's a little clumsy on the calculator, and I'll show you here. So given this example here, so this is a software company. The new version of their operating system will crash less than 6 times per year on average. A system administrator installs the operating system in a random sample of 41 computers, that's N. The standard deviation of 3.6, so that's our sample standard deviation. Sample mean of 7.1, I skipped a line there. So then to use sample mean of crashes is 7.1 with a standard deviation of 3.6. Can you conclude that the vendor's claim is false? So the way we're setting this up, now they just said the vendor's claim is false, but the way they set their hypothesis is the null is that the vendor's claim is true, the mean equals 6, and then they're saying that they're claiming it's more than that. If it's less than 6, we don't care. Their claim was actually less than 6. So even though we wrote equal 6, it really is saying less than 6, or less than or equal to 6. So alternative is more than 6. So difference level of 0.05. Now if I wanted to find the critical value, this is a one-tailed test because this is greater than. We're finding this alpha here of 0.05. What is the critical value that cuts this off at 0.05? So on the calculator, if we enter distributions in their t inverse here, so 4. If we put in, now remember we're looking at less than for the t function, this is actually 0.95, can we this down in here. So we're going to enter in as 0.95, but we have to enter our degrees of freedom. Sample size is 41, so the degrees of freedom is 40. We get 1.684 is our critical value. Now they're looking at the table, right tail area, 0.05, 40 degrees of freedom, that's why they use the 41. Very typical when they're doing a t-test is to give you 41 or 36, so when you subtract 1, you get a nice round number, a nice number that will be in the table. So the 1.684, which is exactly what I found on the calculator. Calculate our test statistic. 7.1 minus 6 over 3.6 divided by the square root of 41 gives a test statistic of 1.957. Now, since that on our curve, I'm going to go back to the curve, 1.957, this is 1.684 here. 1.957 is out here. So we are in that rejection region out here on that upper tail. So we will reject that null hypothesis. So we reject the null hypothesis. We will conclude that the mean number of crashes is greater than 6 per year. So again, here we did all the same things. We did the hypothesis testing when the population standard deviation is not known. We did both p-value and critical value, and we looked up p-values in the table. Again, I don't recommend using the table for p-values. Use the calculator. So I'm going to pause here for a second when I pull up the next part. Okay, so just like with confidence intervals, there's a slight difference when it's a population proportion that we're testing. So we're looking at testing the proportion of p-values and critical values again. We can do either one. So let's look at the p-value method. So here we got the college students have surveyed 90% of female students rated the network site Facebook is cool. The other 10% said lame. So assume that the survey was based on a sample of 500 students. Marketing executive at Facebook wants to advertise the slogan, more than 85% of female college students think Facebook is cool. So what they're saying is this sample of 500 students where 90% of them rated it as cool, is that large enough that they can really say that at least 85% think it's cool? So the null hypothesis is going to be a tough one here. The null hypothesis is going to be less than 85 or 85%. And they want to be able to say more than 85. So let's look at our process here. P is a population proportion. X is the number of individuals who have that specific trait or are in that category. N is the sample size. So P hat is, from our sample, that X from in the sample, the number in the sample that have that characteristic, divided by N, which is the sample size. We have to meet those same requirements again. We must have a simple random sample. The population must be, well, this normally distributed doesn't really fit with a proportion, but the population must be at least 20 times as large as the sample, just like in the confidence intervals. Population must be divided into two categories, either in has the characteristic or does not have it. And then both n times p and n times 1 minus p must be at least 10. So there must be at least 10 people that are in the category and 10 people that are not in the category. So we have to have, usually for doing a proportion, we have a significantly larger sample we are dealing with. And we have our tails here again. Our test statistic is the difference between the p-values. Remember, the standard error for proportions is a little different. That square root of p times 1 minus p over n. And our tails work out just the same. So let's actually go back to our example now and see where this one takes us. So in 2009, it's the same thing. So what are our null hypotheses? Well, the null hypothesis, the mean is 0.85. And the alternative, is that the mean is greater than 0.85. So on our curve, this is a right-tailed test again because our alternative is greater than. And we're going to do this with a p-value. So we have a simple random sample of students. We've met the qualifications. Here's basically what we're saying. Members of the population fall into two categories. The sample size is large enough. Hopefully the population better be more than 20 times 500. There better be more than 10,000 people in the population, and there are. And if the null proportion is 0.85, a sample of 500 would give 425 that are in and 75 that are not. So both of those are bigger than 10. So it's okay to go ahead and do our test here. So there are hypotheses, just like I said. The null is the proportion is equal to 0.85. The alternative is the proportion is greater than 0.85. Significance level is 0.05 that we're going to use again. Again, alpha of 0.05 is pretty standard. Create our test statistic. 0.90 is what we got from the sample proportion, minus the 0.85 is our hypothesized proportion, over the square root of, we use the hypothesized proportion here since we have it, 0.85 times 1 minus 0.85 over 500, giving us a test statistic of 3.13. So remember, proportions, we're always using the z distribution, always the normal. So alpha of 0.05, we're doing critical value, we'd be doing the top corner here to find a z value that was the borderline there. But here we're just going to compare to a p-value. So we got that test statistic of 3.13. What's the probability of being greater than that? So back to normal here. 3.13, comma, positive infinity. That's extremely small, 0.00087. This is 0.0009 is what they're rounding it to. So definitely the p-value is smaller than 0.05. So we reject the null hypothesis and conclude that, yeah, more than 85% of female students think that Facebook is cool. This is just using the calculator, so I'm going to put this information in the calculator. We're going to do stat, tests. Number 5 here is one prop z test. That's what we want. So our p0 is our hypothesized proportion. That's 0.85 from our null hypothesis. X, well, it just said 90%. So I'm going to put in here a sample of 500 times 0.9. It's 450 that said that were in that category that thought Facebook was cool. Now, if that comes out to a decimal, sometimes the calculator will return an error depending on which version of the calculator you have. You may have to round that up or down. Then N, of course, is 500. Our alternative is greater than, so that's the alternative that we want. Hit calculate. And there it is. 8.7 times 10 to the negative fourth, or 0.0009 is our p-value. And there we go. Shows their printout right there. Same one we had. Okay. Test hypothesis about a proportion using the critical value method. If we were going to use the critical value method for this test, as you can see, we put alpha on our tails. This is an upper tail. So we put 0.05 here and figure out what this boundary value is. We've done this several times. We're actually looking at 0.95 here because that's on the top tail. So it's 100 minus the 0.05. So 1.645 is going to be our critical value. And that's what they're showing here, is going through their testing to make sure everything qualifies. So we have this in the job adults created that only 50% of them are satisfied with their jobs. The president believes that more than 50% of his employees are happy with their jobs. So he does the test to see. So a simple random sample of 100 employees, and 54 report that they're satisfied. So is 54 enough? Well, first of all, we have to look. This is a simple random sample, so we're good there. The sample size of 100, is it more than 20 times? Are there at least 2,000 employees? Well, we don't have that information here. So we're going to assume it's true. We've got 50, of course, we've got 100. If we hypothesize proportion of 0.5 or 50%, sample size of 100 would give us 50 that do like their jobs. That's more than 10, and it would give us 50 that don't, so that's more than 10 as well. So we meet that category. So if the total number of employees in the company is more than 2,000, we're good. Like we said, we have to assume that because we aren't told. So then here we found our critical value just as we did, 1.645, and the test statistic, we've got 0.54 minus 0.5 over, we're using the hypothesized value down here, 0.5 times 1 minus 0.5 over 100. We'll get a test statistic of only 0.80. That is not outside. So on our curve here, 1.645 is here. This is our rejection region. 0.80 is somewhere in here. So we're not even close to rejecting. So we know we did not reject. So our statement here is to fail to reject, because 0.80 is not in the rejection region. So we did not reject HL. So there's not enough evidence to conclude that the company's president is correct in his belief that the proportion of employees are more than 50% are satisfied in his company. So again, we went through all those steps. We did a test with p-value and a test with critical value for population proportion. The biggest thing here is we have to get those assumptions. We have to make sure we're meeting those assumptions. Now, I can tell you this on a test, probably won't give you an example where those assumptions aren't met. Otherwise, it's a really boring question. Because all you'd have to do is write down, can't do this. So on a test, I will always give you questions that the assumptions are met. Still good practice to do it. On the homework and maybe the quiz and Connect, there's a good chance that at least one of those will not meet those assumptions. So be careful. Okay, once again, I'm going to pause for next PowerPoint here. So the last one here, just like dealing with the confidence intervals, I want to take a minute to describe how do we know which test to use. Well, first thing we need to decide is, are we looking for a mean, trying to do a test for the population mean or the population proportion? So is it a population mean, mu, or a population proportion, p? Next, if it is the mean, then we have to know the population standard deviation. If we do not know the population standard deviation, then we have to use the t-test. If we do know the population standard deviation, we're going to use the z-test. For a proportion, we're always going to use a z-test. Here's our little chart. Now again, if the sample size is less than 30, the population must be approximately normally distributed. If not, then we're not going to be able to test it with what we learned in this class. If it's not approximately normally distributed and if you have that sample smaller than 30, it requires what they call nonparametric methods, and we're not going to deal with that. So that's why it says consult a statistician there. So there you go. That's very quick. To determine which method to use, is it a mean, population mean, or population proportion? Population proportion, as I said, is always a z-test. If it's a mean, do we know the population standard deviation? In which case, it's still a z-test. If it's a mean and we do not know the population standard deviation, then we use the t-test. So that is it for this week. We'll close that out. If you have any questions, please let me know. Otherwise, have a great week.